Okay, let's start talking about the extreme value theorem. So this is another value theorem, and it's broken down into two parts like all the value theorems, extreme and value theorem. So what does extreme mean? Extreme means like the biggest value you can take, the most extreme value you can take, or the largest value, and it could also be the smallest value, or the most negative value, or the smallest value in all. And those are the two extremes. We have the highest and we have the lowest. And we're going to be talking about that in terms of graphical explanations and some definitions. Not really too much of mathematical and calculus, just getting the idea of what the extreme value theorem says in the first place. And we talked about the highest and the smallest. What it says is if f is continuous on a closed interval from bracket a to b in brackets, then f has both a max and a minimum value on that interval. And it's very specific in its definition, like all the value theorems. It has to say continuous and on a closed interval. So continuous and closed, what does that mean? Continuous and closed. Actually, let me just make some more space because I'm actually going to do two examples side by side. Let's say I have this function right here. It looks something like this. Notice that it is closed interval and is continuous throughout this interval from a to b. The extreme value theorem, if we apply it to this function, says that because it is a closed interval and continuous, there is a maximum and minimum value of the function, and that happens here. This is the max value, and the minimum value, which is here, which happens here. So whatever those values are, that's the max value and the minimum value of that function. And it's also not limited to being inside the interval. It can actually be at the endpoints of the interval. That's why closed interval definition, the closed aspect of it, makes it super important to actually know. Here's an example of a closed interval being, or the endpoints of the interval being actually the max and minimum value. See, now this is the maximum value and this is the minimum value. And then of course there can always be some in between type of thing where it's could be the endpoint being the minimum, but then somewhere else is being the maximum. So here's the minimum and here's the maximum. So now let's try to tear down this theorem and see what happens when we change it to not continuous or an open interval, and see how this definition starts to break down. The first one we're going to look at is not continuous. And if it's not continuous, we can't guarantee to be a max or a min value. Here is an example. If I have a function that looks like this, let's say like this, and then here it's like that, and it's defined on A. Let me draw the axes. Let's say it's defined here A and defined here B. So let me just draw A and B. There is no minimum value. It is not guaranteed to be a minimum value, because if we look down this curve, where this hole is, or this discontinuity, there would be a value, but it's not. It's discontinuous here. It's a discontinuous function, and because of that, we cannot guarantee there to be a minimum value. I guess many people would think, what happens if we just go a little bit right or a little bit left? Notice that that's not what discontinuity says. It's not defined at that exact point, but we can get really, really close to it. Let's say this is, for example, 2. We can go 1.99. Feels like that could be the minimum, but we can actually go even further, 999.9, and that's even closer to the minimum, but we're never going to get to that minimum fully because we can just add an infinite number of 9s, And we can't really use a limit because it's not defined here at all. So we can't say it has a defined minimum value. So it's not continuous, it breaks down. Let's look at open interval. That's the second way it can break down. Open interval, so now instead of the brackets we have parentheses. And what does that look like? Okay, so same argument here. If this is A and this is B, there's not guaranteed to be a max and a min value because we can get really close, but we're not going to get there, so there's always going to be some smaller value as long as we keep adding the value, like the value point, let's say this is 0.000001, we can always get closer by adding more zeros, so we can never get there. There's no defined minimum value, and same with this value, there's no defined maximum value. So the extreme value theorem breaks down. So we need these two conditions. It needs to be continuous and it needs to be a closed interval to be able to be, I guess, for you to use the extreme value theorem. And then there's a second part to the extreme value theorem, kind of like the second part. This is like part two, extreme value theorem. It talks about local extreme values, or the way we actually say is called extrema. That means both max and min. We're talking about local, and this idea of locality, or like something nearby. Local means nearby. Let's say I have something that looks like this, and it's defined on these endpoints. If we use the extreme value theorem, it's guaranteed to be a max and min, but now we're looking at something called a local min and a local max. And basically what it says is that even if there's not a max or a min, like a absolute max or min, like the highest and the lowest, there's kind of like mini max and mins in a neighborhood nearby. If I took this neighborhood here, it looks like this is the max. If I took this neighborhood here, this is the minimum, a type of minimum. Same thing here. If I take this neighborhood here, there's a minimum. And that's the idea of local max and local min. So we call this a local max because it's not the highest. Here's the highest. And then let's say this one's a local min. And then this is even lower than the local min, I guess, if you really want to. So we give this a specialer name, absolute min, meaning it's the lowest of the whole thing. And then this would be called the absolute max. So local is not necessarily the highest, but it is one of the high points. And local min is one of the low points, but it's not necessarily the low points. And all these local max and min actually have something in common. Notice that the derivative is 0 at these points. And that's the idea of local extreme values, that we can actually find local extreme values easily by finding where the derivative of the function is equal to 0, and if we find all the x values, we can find where the possible local max and local min is. And this process of finding local max and min, and also absolute max and absolute min, is actually it's very detailed in that there's actually pretty much the rest of derivatives is focused on finding local maxes and min. The applications of derivatives, they're basically focused on this idea, and we're going to use extreme value theorem to actually show, and calculus at the same time, to show where to find local maxes and mins and how to actually determine if they're local max or mins, just finding the derivatives. So we have this first fact that we can find points where it's 0 and we can either be local max or local min. We call these critical points, critical, because these are values where there's going to be a possible extrema. And we're going to get to more detail about that, but we're just looking more into the basics of the extreme value theorem. So again, just a recap, continuous and closed. It has to be continuous and closed. If that is true, then there will be a maximum value the function will take on, and a minimum value will take on. And that could be in the interior, it could be at the endpoints because it is a closed interval, or it could be a bit mix of both, an endpoint and an interior point. And notice we just break down the definition and it just doesn't work anymore if we have not continuous or discontinuous right here, or an open interval. And then the second part of the extreme value theorem is thinking about local extrema, where it's kind of in that neighborhood is going to look like a max or look like a min, but not necessarily be the highest or the lowest value. We give those two special names. The local mins are in a neighborhood, but the absolute minimum is the lowest value of the whole function, and then absolute max and local min are very similar. And then we can actually find local min and max pretty easily just by finding where the derivative is 0, and we call these critical points, but we're not really going to get into detail about critical points until a future video because there's so much to talk about with critical points, so it's best to save that for later. So with that, that's the end of the video. Hopefully these graphical explanations are helpful, especially getting into the mindset of these value theorems, because saying it with words can be really complicated, but showing it through a picture or having a visual reminder is much more helpful, especially to me, and hopefully it's helpful to you. So that's it for this video.